This is 12.1.3, Thomson's experiment for specific charge. Now, just before we move on, quick recap. Anything in physics that's specific means per unit mass. It's a very important thing to keep in the back of your minds because there's so many people who actually don't know what the word specific means in physics. So, specific mass is given by E over m or Q over m. So E over m is specific charge, or also called the charge to mass ratio. Now, Thomson, he made electrons do circular motion in a magnetic field. So just as a reminder, we call these B fields. So let's sketch, first of all, a uniform B field. And we'll draw electrons doing circular motion in this B field. I can draw these electrons at different positions. So remember, if you wanted to verify that this is the way that electrons are going to move, use Fleming's left-hand rule. And the current is in the opposite direction to the motion of electrons, because electrons are negatively charged, and conventional current is a movement of positive charge. So if you do Fleming's left-hand rule, your index finger points into the plane, and you need to rotate your hand around such that your middle finger points to the opposite direction of each of the arrowheads I've drawn. So you can see at the top, we experience a force going vertically down. Then on the right-hand side, we experience a force to the left. At the bottom, we experience a force to the right. And on the left-hand side, we experience a force directly to the right. So they move in circles. According to Fleming's left-hand rule. Which is the motor effect. And we can tell that they're going to move in circles because force is always perpendicular to the velocity of the electrons. And if it's always perpendicular to the velocity of electrons, it means it's a centripetal force so therefore circular motion. So, we can then make an equation that relates the force due to the magnetic field to the centripetal force. So we say that BeV, or BQV, in this case because electrons BeV, is equal to mR omega squared, which is centripetal force, then we can rearrange this equation to get E over m, which is our specific charge. So it's R omega squared over BV. Now if you recall that omega is equal to V over R, here we've got R over V, so that's 1 over omega. So that gives us E over m is equal to omega over B. Now, problem is, Thomson didn't have the means to measure the frequency, and by extension, the angular frequency. Start a new page. So, at this point, Thomson doesn't know the charge of an electron. He also doesn't know the mass of the electrons. So Thomson did not know E or m. So that means he can't use the electron gun equation, because you have to know the charge and you have to know the mass of the electrons to use it. What he could do, though, is he could play around with electric fields. So if he's got two parallel plates, plus and minus, in between those plates he'll put a fluorescent grid. And then if he directed his cathode rays in between these fields, he would see that the electrons would deflect like a parabola. So the electrons behaved like a projectile. So path of electrons in the E field is a parabola. So it behaved like a projectile. That means that in between the plates, the only acceleration that the electrons experience was a vertical acceleration, which in this case was upwards. Normally when we talk about projectiles, we talk about things falling under gravity. So acceleration is down. But in these E fields, it's up. So if we draw another pair of plates, if you have a pair of plates, we know the potential difference because we can, for example, set the top plate to a known potential difference and have the bottom plate grounded. So the potential difference between the plates is known. Then we can measure the separation of the plates. That's doable. We know that the force experienced is EQ. And this is vertically. We know that there's constant velocity horizontally. So acceleration is only vertical. Now the electric field strength E, he can get that from V over D. That's fairly simple to do. So next what Thomson did is now he took both an electric field and he took a magnetic field and he crossed them together, perpendicular. So Thomson then crossed E and B fields. So if we've got our plus V 0 and we put our magnetic field there. So now what happened is when the electrons came to these plates, they continued horizontally without a deflection. So he adjusted both his fields until he got this effect where the electron just passed straight through with zero deflection. So what was happening here? The electrons experience a force upwards due to the electric field. So that's F subscript E. But due to Fleming's left-hand rule, they also experience a force downwards due to the magnetic field. F subscript B. Now if the electron passed straight through with zero deflection, it meant that the force upwards due to the electric field and the force downwards due to the magnetic field were equal to each other. So now all he had to say was, okay, so FE must equal to FB. And he knows that the electric field strength, E, is equal to V over D. So now he just had to make substitutions. So Fe, that's EQ, is equal to FB, which is BQV. And he knows that E is equal to V over D. So here we get QV over D equals to BQ little v, which is velocity. The charges now cancel out. So now that the charges cancel out, we can rearrange this to find the velocity. So V equals to B, big V, sorry, that's incorrect. It's V over BD. Now, we know that E over M, so we know from before that E over M is equal to omega over B. We also know that omega is equal to V over R. And omega is equal to V over R. So now we can make a substitution for omega and put V over R. So E over M is equal to omega, which is V over R, that's V over RB. But we just said earlier that V equals to big V over BD. And so we make these two substitutions. And we substitute for V. So the specific charge is then given by E over M is equal to V over R times B times B times D. So that's V over B squared RD. Now, Thomson would know the potential difference between the plates. Thomson would know the magnetic flux density. He could measure the radius of the circle by using a traveling microscope, for example. And he knows the separation of the plates. So now with all those things that he could measure at that time, he's got a value for the specific charge. Now despite that, we still don't know the mass of the electron, and we don't know the charge of an electron, which was discovered later by someone else called Millikan. And that's the end of 12.1.3.